In part 2 of the lecture, we will be looking at confidence interval. For population mean, we already covered when the sigma is known. We will now move to when sigma is unknown. In real life, most of the time, we will not be knowing the sigma of the population. So that is why this part will also be very useful. How do we calculate confidence interval for mu when sigma is unknown? If the population standard deviation sigma is unknown, we can substitute the sample standard deviation, which is denoted by S. But when we do this, this introduces extra uncertainty, since S is a variable from the sample, is variable from sample to sample. So what we can do is we can use a distribution called the T distribution instead of the normal distribution. To use this distribution, the assumption is population standard deviation is unknown, the population is normally distributed, and we will use this student's T distribution. This T distribution was actually developed by a guy called William S. Gossett. He was an employee of Guinness in Northern Ireland. During his days, they were not allowed to publish under their actual name. So he used a pen name called student. So that's why the T distribution has a student's T distribution. Okay, the formula for confidence interval estimate is given in this form. X bar plus minus T alpha divided by 2. S is actually the standard deviation of the sample, square root of n. If you see, the formula is exactly the same as the formula we used earlier, but the only difference is now instead of the sigma, we are using the standard deviation of the sample. Okay, the student's T distribution is a family of distribution where the T alpha divided by 2 value depends on degrees of freedom, which is called the DF. So the degrees of freedom is calculated by the number of sample minus 1. Why is that so? We will look at the next slides. Okay, why do we calculate these degrees of freedom? For example, let's suppose the mean of 3 numbers is 8. And we have 3 values here, right? 7, 8, and the last number is unknown. So if we already know number 1 and number 2, and since the mean is 8 for 3 numbers, so the total is 24. So 7 plus 8 is already 15. So the last number, it will not vary. It will always be fixed. So the number should be 9, right? Okay. So that's how degrees of freedom comes into this formula. So for n equals to 3, the degrees of freedom is n minus 1, which is equals to 2. So what this table tells you is, if you are given 3 data points, when you already know 2 values, the last value is not free to vary for any given mean. Okay, the T distribution is similar to your normal distribution. The normal distribution is given here, right? Okay, but if you see here, there's degrees of freedom, 5 and 13. When the degrees of freedom is small, which means the sample size is small, the distribution is actually like this, which is far away from your normal distribution. But as the sample size increases, which is now 14 minus 1, right here, so the distribution becomes more normal. So as your sample size increases, the T distribution will follow the Z distribution. So the table that we will use for all our calculation and in exams will be this table I've already given you, which is in appendix. So this table will have what we call as areas in both tails combined. So if your alpha value is 5%, you will look at this column here, which is 5%. If your alpha value is 10%, you will look at this column. And if your alpha value is 1%, you will look at this column. So the degrees of freedom is given here. It will start from 1 to 60, and after 60, between 60 and 120, you can use the 120. And if your sample size is more than 120, the t distribution will follow the normal distribution. So how do you look at the student's t table? This is an excerpt from the table given before. In our example, we have n equals to 3. So the degrees of freedom is n minus 1, which is 2. Alpha level is 10%. So we will look at the column called 10% because the both areas, here 5%, here 5%. So 5 plus 5 equals to 10%. So the column here 10%, degrees of freedom 2, and the number that you get here is 2.920. This will be used here in the, this is what we call as the critical value. Okay, here the table is slightly different from what you got in your normal distribution. The numbers given inside the table here are not probability values. They are actually t values. Okay, this is a summary of all the confidence level and also the t value that you will get from the table. So if you see here, confidence level of 90%, if your degrees of freedom is 10, you get a t value of 1.812. 95% you get 2.228, 98% 2.764, and 99% you get 3.169. So as the sample size increases, the t value will follow your z value. This is the last column here, right? This column here. If your sample size is more than 120, the t values here are actually the same as the z values. So let's say we look at an example which gives you this scenario. A random sample of size n equals to 100 of travel times has a mean and standard deviation of x bar equals to 110.27 and a standard deviation 28.95. Form a 95% confidence interval for mu. So here some of the numbers that we can summarize here is we have an n equals to 100, x bar equals to 110.27, the s equals to 28.95, and the degrees of freedom is n minus 1, which is 100 minus 1, 99. So since we don't have a 99 in the table, we will look at the next number, which is 120. Okay, so the t alpha divided by 2 for a 95% confidence, the t value is 1.980. So the formula for calculating the interval for mean when the sigma is unknown is given here. X bar plus minus t alpha divided by 2, standard deviation divided by square root of n. So the x bar is 110.27, which is here. The s is 28.95 here. N is 100, given also in the question, 100. And the only number that we got from the table was the t value, which is 1.980. So when we use this formula to calculate, we will get a lower limit of 104.54, and then you have a mu, and then the upper limit will be 116. Okay, how do we interpret t-distribution confidence interval? Interpreting this interval requires the assumption that the population you are sampling from is approximately a normal distribution, especially since n is only 25. This condition can be checked by creating, the first one is looking at the normal probability plot or the box plot. So the normal probability plot you can get from the software called as SPSS. You can run descriptive and then you can get this, or descriptives and explore. We can also get the histogram by using descriptives, and then there's another function called explore. So that will tell us whether they are normally distributed. So for this PP plot, if the points are all very close to the line, then we can use we can conclude that the distribution is quite normal. Whereas for the histogram, we see the Q1 and we have a Q1, then we have the lower limit here minimum, the maximum, and then the Q1 and the Q3, and this is your median. So when they are distributed like this, then we can conclude we have a normal distribution. So next we will look at an exercise which is exercise 3, and I will also show you how we can solve this exercise. So in this exercise, the sample size is given as 100. The mean value is 1500. This is X bar, and this is your S, which is your standard deviation of the sample. What we are required to do is to construct a 95% confidence interval and then interpret the interval we construct. For answering exercises, I would suggest you to summarize the values given from the question before we begin calculation. So the X bar given was 1500, S was 200, N was 64, and the confidence interval is 95%. The degrees of freedom is 100 minus 1, which is 99. So since we don't have a degrees of freedom 199, we only have 60 and 120. We will look at the row where we have a degrees of freedom 120. For 95% confidence, the t value is 1.980. So the formula X bar plus minus T alpha divided by 2 S divided by square root N. 1500 plus minus 1.98 times 200 divided by square root of 100. We get 1500 plus minus 39.6. So the lower limit is 1460.4 and the upper limit is 1539.6. So what we can conclude from this interval is we can be 95% confident that the population mean spending for all Amazon Prime member shoppers is somewhere between 1460.40 and 1539.6. You can try this exercise for on your own. Later I will also post the answers on the e-learn. Okay, next we will look at confidence interval, but this time we will move from mean values to population proportions. So when we calculate confidence interval for population proportion, which is denoted by a pi, so why we calculate an interval estimate is an interval estimate for the population proportion can be calculated by adding an allowance for uncertainty to the sample proportion, P. Recall that the distribution of the sample proportion is approximately normal if the sample size is large with standard deviation given as sigma P equals to pi times 1 minus pi divided by N. We will estimate this with sample data, which is P times 1 minus P divided by N. So the pi is now replaced by the P. So the confidence interval calculation for proportion, we will have this formula, P plus minus Z alpha divided by 2 square root of P times 1 minus P divided by N. So what is 1 minus P is the proportion of failure. So P is the proportion of success, 1 minus P is the proportion of failure. And one of the note you need to take care of is N times P should be greater than 5 and N times 1 minus P should also greater than. Next we'll look at an example which gives you a scenario where a random sample of 100 people shows that 25 are left-handed. Form a 95% confidence interval for the population proportion of left-handers from a 95% confidence interval for these left-handers. So the formula we will write here is P plus minus Z alpha divided by 2 square root of P times 1 minus P divided by N. So here the P value is already given here, 25, right, out of 100. So 25 divided by 100, you get your P. Your Z alpha divided by 2 is 95%, you get a Z value of 1.96. Then we have a proportion 0.25 times 0.75, which is 1 minus P divided by 100. So we will get a lower limit of 0.1651 and an upper limit of 0.3349. What we can conclude from here is we will be 95% confident that the population percentage of left-handers is between 16.51% and 33.49%. Okay, although the interval from 0.1651 to 0.3349 may or may not contain the population proportion, 95% of the intervals from these sample sizes of 100 in this manner will contain the population proportion. Next, I will walk you through this exercise number 5, which is given in your page 325, exercise number 8.28. And this is a question which looks at the cell phone provider, and they're thinking about providing a new phone at a reduced cost. What they want to find out is if they offer the new cell phone at a reduced cost, will the subscribers change or upgrade? So the question gives you that the sample size is 500, which is N. The proportion the number that will change or upgrade is 135. And what you are asked to do is to construct a 99% confidence interval, and based on this interval, how the findings can be used by the manager in charge of promotional programs. For answering exercises, I normally suggest you summarize the values given first. So the values given are P equals to 135 divided by 500, you get a 0.27. 1 minus P is 1 minus 0.27, which is 0.73. N equals to 500, and confidence interval is 99%. For a 99% confidence, the Z value is given as 2.576. You can also round it up to 2.58. So then what we will do is we will write the formula, which is P plus minus Z alpha divided by 2, P times 1 minus P divided by N. So the P value is already given, P proportion value is already 0.27 plus minus 2.576 times 0.27 times 0.73 divided by 500, you take the square root and you get a lower limit of 0.2189 and an upper limit of 0.3211. So the next question is how can we use this information for the manager to decide on promotional program. So this is how you answer them. The manager in charge of promotional programs concerning residential customers can infer that proportion of households that would purchase a new cell phone if it were made available at a substantially reduced installation cost is between 22% and 32% with 99% confidence. Exercise number 6, you can try it on your own. I will also provide the answers later in the e-learn. So we will stop here for part 2 and we will continue to part 3.